This is our glider project by Noah Ramirez and Thomas Forster for AE 1601. So for the project requirements, we had to be able to fit the glider in a 16-inch by 16-inch box. It had to fly at least 20 feet. It had to be hand thrown, and we made it out of balsa wood. And to make sure we met all these criteria, we manufactured and tested it, and we made sure that we got consistent results and threw them at the same distance every time. And a big focus we had to project on was that it had to be stable. So we glued it together, and we had to make sure that everything was in place and it remained intact. So for our initial design, one of our major focus was exploring the changes in wing and stabilizer geometry. We experimented with elliptical wings, which provide excellent aerodynamic efficiency by minimizing induced drag, but we found them more challenging to design and construct compared to just a simpler rectangular or tapered shape. So for our horizontal stabilizers, we tested both of these, the elliptical design and just the square or rectangle ones, and we ultimately favored the regular ones over practicality. And we saw that it would have had generally the same result, so we thought, why not do that? And for the tail configuration, we debated between a conventional tail and a T-tail stabilizer. The T-tail has advantages like improved airflow over the horizontal stabilizer and reduced interference with the wings, but it has a higher center of gravity, which can make the glider less stable. So we opted to a conventional tail because it was more simple, reliable, and it just aligned better with our project goals. And another key part that we had to see in different iterations was the weight distribution. It was easy, to put Play-Doh, which we ultimately did, but another option we were looking into was lead tape, which could have been more permanent but also consistent, but it would have been more expensive, harder to attach aerodynamically. And so in the end, we chose for Play-Doh because it was easier and you can mold it so it's aerodynamic. And for our iterations, we started out actually with the middle picture where it was just a rectangle for the wing and a rectangle for the back horizontal stabilizers and vertical stabilizers. And we ultimately moved on to the basically second and third where we tapered it and also made the vertical wing tapered.
Sizing was just a matter of doing a lot of research beforehand, so we found out that we needed the aspect ratio, which is the ratio of the wingspan squared to the wing area, to be high in order to reduce drag. So we kept the wingspan as long as possible at 16 inches. In order to cut down the area, we tapered the wings. We did some research on taper ratios and found that the most optimal would be somewhere from 0.4 to 0.5. We decided on 0.5. We decided to taper the leading edge because this leads to more stability at lower flight speeds we expect. The root cord, we kept the same size for ease of manufacturing and so that we would have more surface area for glue to attach the wing onto the fuselage. We placed the wing based on the distance between the stabilizers and the wing. This is another thing that we researched, so we found out that that distance should be 2 times the root cord length. We found out that the horizontal stabilizer should be 1/4 the area of our wing. We chose a rectangular shape because this seemed like a common choice. The vertical stabilizer should be 1/10 that, and we chose triangular as this seemed also a common choice and it was easy to manufacture. We decided to put the vertical stabilizer on top of the horizontal stabilizer. We also talked about that to avoid raising the center of gravity and to avoid having any moments generated from exposing the horizontal stabilizer to more air. As far as testing goes, we did 2 different stages of testing using our first iteration, which was assembled using tape. It was not very stable because the tape did not keep things in place, and so the most glaring issue that was caused because of this is that the glider kept pitching up instead of gliding forward. We were able to alleviate this temporarily using more tape and adding weight at the nose. That made it more stable, and we began working on throwing technique. We were pretty surprised at this stage by the durability of the balsa wood, and we decided that we should keep adding tape to our final design. Our max flight at this stage was around 65 feet. For our second and final iteration, we added more mass onto the nose, more Play-Doh. We manufactured the wings again as carefully as possible, and then we were able to glue them. We sanded a bunch of sharp points on the glider to reduce drag. On our first round of gluing, the stabilizers did not stay glued, so we had them taped. We conducted more testing. We were able to consistently attain around 40 feet flights, which we weren't able to do beforehand, and we continued testing. And our stability of our flights continued to do pretty well. This is our final design as modeled in SolidWorks. You can see that there is a tapered leading edge. We have the rectangular horizontal stabilizer and a triangular vertical stabilizer. Our real life pictures of our final design, they match up pretty closely besides the fact that we sanded around all the sharp points. This is our glider within a 16 by 16 box, and the center of gravity was located 8.6 inches from the back end of the fuselage. The quarter cord was located 10.53 inches from the back end, so the center of gravity is behind the quarter cord. And then these are our formulas that we use to calculate the coefficient of lift and coefficient of drag. We ended up getting for the drag coefficient 0.066 and the lift coefficient was 0.198. These were based on a couple assumptions that the lift equaled the weight for the flight. We had to take a lot of averages from various sources for different values like the efficiency factor. Here's our flight video. So this is our best flight.
And so for our conclusion, I would say we did relatively a good job. We flew at 55 feet maximum, and also our results were consistent. But some things we could have worked on were definitely making dihedral wings for it to have a greater lift and be able to throw farther in the air. We could have also worked on stability.
And then these are our references and our reference for the images used in our slide.